Good afternoon, ladies and gentlemen. Good afternoon, my dear students. Welcome back to this course, ENE 474. As usual, I will start with some brief, maybe not so brief reminder what we discussed last time. So we started a new topic, which is related to transformers. And in transformers, we use paramagnetic cores. They also use in many different equipment in power engineering. And they're used for the reason that they have high magnetic permeability. And so they increase electromagnetic coupling between two coils. And in this way, they reduce the stray magnetic field and consequently reduce the negative effect of electromagnetic interference. However, paramagnetic cores are associated with some negative effects as well. So, usually if you have two coils and you would like to increase the electromagnetic coupling, this will be one coil, I will call it primary. This will be another coil, I call it secondary. You will put this coil around the same paramagnetic core, which has high magnetic permeability, mu sub C, and subscript C stands for core. And it's much larger than the magnetic permeability of free space. As I pointed out, this paramagnetic core associated with two negative effects. The first negative effect is related to hysteresis. So it's typical for paramagnetic materials. In the simplest, very simplest manner, if you change magnetic field periodically between some maximum minimum value, the hysteresis loop will be formed in the relationship between the magnetic flux density and magnetic field. And this formation of hysteresis loop associated with losses, power losses. And these power losses, as was pointed out first by proportional to the frequency with which we vary magnetic field, proportional to the volume of the paramagnetic core, and they're proportional to the area of the hysteresis loop, enclosed by hysteresis loop. So in order to reduce these losses, people use so-called soft magnetic materials with narrow hysteresis loop. And consequently, H sub H, the area enclosed by hysteresis loop, will be very small and will be small losses. But there are also so-called hard magnetic materials in which the hysteresis loop is very broad, and they are used for different purposes. Partially they use also in the power engineering. They use, for instance, for the design of permanent magnets, and permanent magnets now are used in the design of motors and generators. And so also ubiquitous. Without it we cannot use the modern technology, for instance, Google. The ubiquitous for the construction of the hard drive, the memory, the disk materials, magnetic disk materials is hard magnetic materials. Another effect, negative effect, is that paramagnetic core has intrinsic conductivity. And when it's subject to time-varying magnetic field, eddy currents are induced. They're called eddy currents because they induce currents and they flow in closed paths. They are not induced because the voltage is applied. They are induced by time-varying magnetic field. And these eddy currents may result in large losses. And the following formula, I gave you the following formula for the eddy current losses. Capital T subscript E. It will be 4.44 squared, where 4.44 is nothing else than the square root of 2 times pi, divided by 12. They will be proportional to the conductivity. They will be proportional to the volume of the paramagnetic core, the square of the frequency, the square of the peak value of the magnetic flux density which is applied or goes through this ferromagnetic core, and the square of thickness of the material. And so, in order to reduce these eddy current losses, there are two options which are used actually in practice. The first is reduce the conductivity, and this can be done by using what's so-called silicon steel to dope silicon with conductivity. Material science people found that if you will do this, the doping with conductivity will reduce, doping with silicon will reduce conductivity, but will not affect much, will not affect at all the magnetic properties, namely the high magnetic permeability. So another option is to use so-called laminated design, which is widely used in power engineering, and not only power engineering. Laminated design. The actual ferromagnetic core is assembled for very large number, very thin laminations, which are isolated from one another, electrically isolated from one another by extremely thin layer of varnish or extremely thin layer of oxidation. In this way, we can reduce the actual eddy current losses by n squared times, where little n is the number of laminations. It has some negative effect as well, because it leads to the compromise of the rigidity of the ferromagnetic cores, and it also results in some noise, which usually observe when you stay next to transformers. So that's what was the discussion, and then we move to the discussion of the transformer. So first I mentioned the transformer is an indispensable in the modern power system, AC power system, because it is used to step up and step down voltage. And we discussed this when I gave you the brief review of power system. However, transformer is widely used in many different applications, such as electronics and so on. And so it is used for instance, for impedance matching purposes, and today I will mention this. It is also used to electrically isolate the source from the load. And there are transformers, as I mentioned, Ethernet transformers, which are used in computers. So these are very special transformers. They're not used to step up and step down voltages. They're used in order to filter out common mode signal. Common mode signal, it's a noise induced in communication network due to the electromagnetic interference. And at the same time to transmit the differential mode signal, which represents the information part of the signal, without any distortion. It's typical. And if you will go in the book, when I start discussing the transformer, I also discussed a little bit Ethernet transformers. It is also now we put on the ELMS the third homework, which is due in 10 days, I believe. And there I also suggested you, as a part of this homework, to read about hysteresis losses and eddy current losses and write short report. And this is in the first part of the book. Then we started the discussion of the transformer, its design. The transformer is a static device in which two or more coils which are called winding are strongly electromagnetically coupled. This strong electromagnetic couple is achieved because you put the winding on the same ferromagnetic core, wound them around the same ferromagnetic core, and use high magnetic permeability. So the ferromagnetic core, of course, is laminated. It is transformer steel. Transformer steel, it means that it's doped with silicon. It's laminated. Power transformers, they have additional features. Why? Because it's extremely high currents in power transformers, and that's winding and high voltages, winding should be isolated, so they're put in metallic tanks filled with refined oils, and refined oils used for two purposes. First is for electric isolation, and second for cooling, because that heat will increase the density, decrease the density of oils, and it will be convection of high oil to the top of the tank, and the cool oil will go down, and it's going all the time. So that's how they use for cooling. So then we started the discussion of single-phase transformer. In single-phase transformer, the primary winding is connected to the pump of voltage. It's from power system, and which results in some primary current. While the secondary winding delivers electric power to the load, which is represented usually by impedance. This is called load impedance, and this is indicated by the subscript S, subscript L, that is the load impedance, a different voltage, and it's called secondary voltage, and different secondary current. And what I did first, I considered so-called ideal transformer. And in the case of the ideal transformer, we use the following assumption. We neglect the resistance of primary and secondary winding. We assume that it's equal to 0. We neglect the leakage flux. We assume that all magnetic field lines are confined to the ferromagnetic core. We neglect the conductivity. In this way, we assume that there are no eddy current losses. We neglect hysteresis. We assume that it can be characterized by magnetic permeability, which is very high and often assumed to be equal to infinity in some calculations. So under this condition, I derive the following terminal relations between the primary and secondary voltage and primary and secondary current. Namely, I derive that the ratio of the primary voltage to the secondary voltage at any instant of time is equal to the turn ratio. We use the notation A for the turn ratio, where A is a ratio of the number of turns of the primary winding to the number of turns of the secondary winding. Similarly, I prove that this formula can be written in phasor form, that in the case when we deal with sinusoidal voltages, the ratio of the phasor of the primary voltage to the phasor of the secondary voltage will be equal to A as well. Then I prove the relations between the primary and secondary current. So at any instant of time, the ratio of the primary current to the secondary current is reciprocal to the turn ratio. It's equal 1 over A. And this formula, in the case of sinusoidal currents, can be written for the phasors. That the phasor of the primary current divided by the phasor of the secondary current is equal 1 over A. Well, that is why I stopped last time, and I mentioned that next I will discuss equivalent circuit of the transformer, ideal transformer. So what we will discuss now, the input impedance. So let us consider that we have this transformer. So usually, when you draw a circuit with a transformer, you will never draw these complicated ferromagnetic cores and so on. People use the following notation. They will draw the primary winding, and they will draw the secondary winding. And to show that these transformers, that they are electromagnetically coupled by the ferromagnetic core, they will put vertical lines here. When I was very young, when I was a student, they used to put 3 vertical lines. Now, I don't know, they decided to use the economy of drawing, and they use only 2 vertical lines. So this is a circuit notation for the transformer. And here will be the load impedance. So we consider sinusoidal regime when the voltage and currents are sinusoidal. And I want to find the input impedance of the transformer. So the input impedance is defined as a ratio of the phasor of the input of primary voltage to the input of primary current. That's what I would like to find. In order to find this, I will use this formula 6, and so I can write that V sub 1 is equal A times V sub 2. Similarly, I will use the formula 8 and to replace I sub 1 by I sub 2. So from formula 8, I will find that I sub 1 will be equal 1 over 8 times I sub 2. Then I will substitute this formula 10 and 11 into formula 9, and I will get that the input impedance will be equal A times V sub 2 will be equal A times V sub 2 divided by 1 over A times I sub 2 phasors. All this will be equal A squared, and the ratio of these two phasors, V sub 2 and I sub 2. And the last step in this derivation is that this ratio V sub 2 to I sub 2, according to the drawing of the transformer, or the equivalent circuit drawing of the transformer, is equal to the load impedance. Consequently, we will find this expression for the input impedance, which is equal V sub 1 over I sub 1 is equal A squared times load impedance, where A is a turn ratio. It's defined by formula 5. Very interesting consequences can be found from this very important formula. The first consequence is equivalent circuit of the transformer, ideal transformer. So I can claim now that the equivalent circuit of this ideal transformer can be represented by as follows, that it will be here the primary voltage, here will be the load, which is equal A squared, times load impedance, and this will be the primary current. So you can ask me why there is equivalent circuit of the transformer. So I mentioned last time at the very beginning, and I will say this time and time again during this class, that electric circuits are used as a models for complicated devices. Because we understand electric circuits better than anything else. They're the simplest object of electrical engineering. In what sense it's equivalent circuit? It's equivalent circuit that V sub 1 and I sub 1 in this circuit has nothing to do with the actual physical design of the transformer. It's a circuit. But V sub 1 and I sub 1 are related with the same relationship as in the transformer, because it gives the expression for the input impedance. And the input impedance is a ratio V sub 1 and I sub 1. In what sense it's equivalent circuit? It preserves the relationship between the primary voltage and primary current. And if you connect the actual transformer, ideal transformer, to the power network or this equivalent circuit, the rest of power network will see no difference. Why? Because it will be described by the same equations. It will be the equation for the power network and additional equation between the input voltage and input current of the transformer. And they are the same for the ideal transformer and for this circuit. In this sense, it is equivalent. So this is a general principle of equivalent circuit. To build any device, and we will use it quite a few times in this class, to build electric circuit which has the same relationship between voltage and currents, input relations, as an actual device. As an actual device. Then it can be claimed that there is equivalent circuit. So this is the first application of this. The second application, as I mentioned, transformer used for impedance matching purposes. And I will give you this example with directly related to power system. So usually you have the generators and power plant, then you step up the voltage, and then you transmit the transmission line, and then the distribution line, and then the load. And so let us consider the following situation. Let us suppose that we have transmission line. And you all study transmission line and ENE 381, yes? You all took ENE 381, and you love this class, yes? It's electromagnetic field series. No? It's a beautiful class, it's a fantastic class, electromagnetic fields. Nothing can be better than this. Okay, quantum mechanics is better. But anyway, so these are the transmission line, and you will put here some load. First I will consider resistive load. And this arbitrary resistive load, is not equal to the characteristic impedance. In general, it's not equal to characteristic impedance of the transmission line, which is given by this formula. If you neglect small resistivity of wires, it's equal to the ratio of inductance per unit length, L sub 0, to the capacitance per unit length, C sub 0. And if it's not equal, it will be two waves here. One will be forward wave, you studied this, and another will be the backward wave, in moving in the opposite direction. But we are not interested in the backward wave. We want to transmit power, that will be only forward wave. And how we can achieve this if we have this inequality? How we can achieve this if we have this inequality? And there is a way to achieve this by using transformers. That is why transformers are used for impedance matching purposes. Namely, that if you will connect the load impedance not directly to the transmission line and through the transformer, and then the impedance which transmission line will fill here, R sub L prime, according to this formula, it will be input impedance of the transformer. And it will be equal, this impedance, ZL prime, across these terminals, will be equal the A squared R sub L. And now you can choose the generation in such way that it will be equal to characteristic impedance. You have this freedom of choice. That is why you use transform. You can use it in a such way, A, that it will be equal to the characteristic impedance. And as soon as you will achieve this equality, it will be only forward way. No power which is generated and transmitted will be go to the load and will be consumed, and will be no reflection, will be no backward wave. Well, you can immediately tell me, Professor, this is quite simple, it's quite interesting, but you assume that the load is resistive. In reality, it is not resistive, and in most cases, the load is inductive load, as we discussed when we discussed, for instance, power factor and adjustment of power factor to 1, yes? So the actual load may be, it will be series connection with equivalent load, as we discussed during the power factor, can be represented by series connection resistor and some inductor. So in this case, And in general, it cannot be equal to characteristic impedance, which is practically a real number. And consequently, will be two waves, forward propagated and backward. So how I can eliminate the backward wave in this case? Again, I will use transformer. I'm probably doing one of the problems which is assigned to you in the home. It's not discussed in the book, but it's one of the homework problems. So what I will use? I will use this transformer. And connect this load, which can be represented as a sequence of resistor and inductor. But you will tell me whatever you will do, it still will be complex number, and here will be a squared of this impedance. It will be complex number, it will not be equal to the real number. How I achieve the matching purposes in this case? I need another trick. Who will tell me what is this trick? This is a simple trick, we already studied it. We studied it when we discussed adjustment of power factor to 1. This is a trick when you will put the capacitor across and choose this capacitor in such way that these all connections across these terminals behave as a resistor. That's what we did in the case of adjustment of power factor. And so at that time I derived that this capacitance should be equal, if my memory serves me, can be given by this formula. If you will choose this, then these loads behave as a resistor. So let's suppose that this resistor of this load will be R sub L prime. And then I will choose a number of turns in such way that it will be equal characteristic impedance. And in this way, what it will be here, that the load will match the characteristic impedance. The load will match the characteristic impedance, and the load will represent input impedance of this transformer. And in this way, we will have only forward propagating wave. So these are general principles. You can see capacitor again used. Capacitor is very useful in power engineering. As I mentioned sometimes, the capacitor here will play another function. During the transient, when this capacitor is not charged, it's like a short circuit. And it will protect the load, because most of the current, high current, will go through the capacitor. Then the same capacitor is used in order to adjust this total impedance to behave as a resistance with power factor equal 1. So you see, it's again very useful. When you will study power electronics, capacitance will be very useful for suppression of ripples. Because power electronic devices, it's a switch mode devices. So this concludes the discussion of ideal transformer. Any questions? You see, this this material will be enough if you will use transformer in power electronics. By and large, I will assume it's ideal transformer. It will be enough. In many other low power applications, it will be enough. For instance, when you will discuss practical Ethernet transformer, it also will be enough, although more the general case is discussed in the book. However, it's not enough in power engineering. In power engineering, we have to see what is a deviation occurred if the transformer is not ideal. If the transformer is not ideal. And so today I will start the discussion of non-ideal transformer. Non-ideal transformer. Oh, I'm better use space there. And it will be based on the coupled circuit equation. So these were assumptions. This is the formula 3 for the ideal transformer. For non-ideal transformer, we will not neglect resistance, so we assume that it's not equal to 0. Secondary resistance is not equal to 0. More importantly, and this is very important, only people in power engineering know this, that this is very important. We will neglect the leakage, magnetic leakage. We will not neglect the flux linkages due to the leakage. So, as I pointed out, in the case of the transformer, we deal with a high magnetic permeability for a magnetic core. And because of high magnetic permeability for a magnetic core, majority of the magnetic field lines will be confined to the ferromagnetic core. However, very small number of them will leak out. Very small number of them will go through ferromagnetic core and air. Ferromagnetic core and air. And this very small number, turns out, they determine the property of power transform. They determine the property of power transform. They will result in so-called leakage inductances. And I would like to challenge you, go and find any other area except power engineering when they deal with leakage inductances. That will result in leakage inductances. That is why this is very important assumption. We still assume that the conductivity is equal to 0, and later on we will get rid of this assumption in some ad hoc way. You will see how it can be done. But at the beginning we assume that conductivity of ferromagnetic core is equal to 0, and we assume that there is no hysteresis. And so these are the main assumptions for the non-ideal transform. So the question is, how we will study this non-ideal transform? And we will study this non-ideal transform by using coupled circuit equations. Coupled circuit equations. So I will use this transformer, and I will write, I consider that we deal with sinusoidal voltage and sinusoidal current. And I will write Kirchhoff voltage law for the primary winding and Kirchhoff voltage law for the secondary winding. And they will be coupled circuit equations because these two coils are electromagnetically coupled. So if I will write the Kirchhoff voltage law for the primary winding, then the input voltage V sub 1 will be equal drop of the voltage across the resistor or due to the resistance of the winding. Then it will be the voltage which is induced in the primary winding due by the magnetic flux created by the current through the primary winding. So induced in the primary winding due to the inductance of the primary winding. And then it will be additional component of the voltage which is induced by the magnetic flux created by the current through the secondary winding. It also creates magnetic field, and it will induce this voltage as well in the primary winding. And it will be equal minus J for sinusoidal current, angular frequency, mutual inductance. These characterize the coupling between the primary winding and secondary winding. You may ask the question why I put sign minus here. In the case of transformers, this sign minus is placed here because we can use Lenz's law. You see that current in the secondary winding is induced by the magnetic flux created by the current in the primary winding. And this induction, according to the Lenz's law, is always in a such way counteracts the cause of induction. What is the cause of induction? The current through the primary winding. But this current exists because the voltage is applied to the primary winding. So the cause of induction is a voltage applied to the primary winding. And that is why we put sign minus. So you can see that in this case, we have three components of the voltages of distinct nature. One is a drop of the voltage due to the resistance, which is assumed non-zero. Another is a drop of the voltage due to the inductance of the primary winding, and another is due to mutual coupling between the primary and secondary winding, which is described by mutual inductance. Similar equation can be written for the secondary voltage. It will be the drop of the voltage due to the resistance of the secondary winding. Then it will be drop of the voltage due to the self-inductance of the secondary winding. The secondary current will create magnetic flux, and this magnetic flux will induce the voltage in the secondary winding. And then it will be the voltage induced due to the mutual coupling between the secondary and primary winding. There is a current through the primary winding. It creates magnetic field, represented by the magnetic field lines, which link the secondary winding, and they, because it's time varying, they will induce the voltage. So here is a coupled circuit equation. The two mathematically coupled because there are two variables in each equation. So they're coupled. Physically they're coupled because of strong electromagnetic coupling between the primary and secondary winding. This is the principle of the transformer. We want to achieve this. These extremely simple equations. And all my discussion will be based on this. And you will be surprised how many things will be revealed from these equations. How many things could be revealed from these equations related to the performance of the transformer. So usually these equations are written slightly different form. Omega delta 1 is what we'll call the primary reactance. We use here 2 subscript 1, 1 because it represents the voltage which is induced by primary current in the primary winding. Primary current in the primary winding. Then we will use subscript 1, 1. Then this product is called the secondary reactance. Again, we use subscript 2, 2 for the same reason. Because it represents the secondary voltage here induced, the voltage induced in the secondary winding due to the magnetic flux created by the secondary current. And this product is called mutual reactance. And we use subscript 1, 2 for similar reasons. So it will be, in the case of the primary winding, it will be the voltage which will be induced in the primary winding created by the magnetic field lines, time-varying magnetic field, another way to say, created by the current in the secondary winding. That is why we use subscript 1, 2. And so if we will use this fact, this notation, we can rewrite this coupled circuit equation in this form. So these are the same equations, but written in terms of reactance. So what I will do next, I would like to investigate what we can get from these equations. If we deal with transformer, we're usually interested what is going on the secondary side, on the side of consumption, on the side of the load, on the side of the customer. In order to do this, I will like to find the relationship between the secondary voltage and the secondary current and the primary voltage, which creates this coupling, which creates the currents. Without it, primary voltage, there is no excitation of the transformer. So in order to find this, what I will do, I will find the expression for this secondary current here. I'm sorry, I misspoke. I will find the expression for the primary current in equation 26 in terms of the primary voltage and secondary current. And then I will substitute it here instead of I sub 1, and I will get this relationship between the secondary voltage and the secondary current, a known primary voltage. So the first step to find the current I sub 1, 1. How I will find it? I will move this term to the left-hand side. Well, if I stand like this, it will be right-hand side. And then I will divide, will factor out I sub 1 and divide by the R sub 1 plus J X sub 1. So if I will do this, I will find that the current I sub 1 will be equal this voltage V sub 1 divided by this coefficient, which obtained by factoring out I sub 1, plus J X sub 1, 2, divided, plus because I move it on this side, divided by the same number R sub 1 plus J X sub 1, 1, and this will be dependent on I sub 2. So I found this from the equation 27. And then instead of I sub 1 here in 27, instead of I sub 1 in 27, I will substitute this expression. So when I substitute this expression, instead of I sub 1 will be this term. So I can write that V sub 2 will be equal. This term comes with minus, so will be this term. So it will be minus I X sub 1, 2 divided by R sub 1 plus J X sub 1, 1. It comes from this term times V sub 1. So I will substitute instead of I sub 1 this expression. So if I will substitute this first term, I have to multiply by this. And then I have to substitute this term also. And then all will depend on I sub 2. So I sub 2 can be factored out. And so if I will, so I will factor out this in simple algebra. So I will get this expression. Again, how I got this expression? When I substituted this first term, it is here. It's multiplied by negative j times x sub 1, 2. Then I substituted this term. It goes with sign minus, yes. It's multiplied by x sub 1, 2, yes. And divide by, so it will be jx sub 1, 2 squared divided by this. And I put this in the denominator because if you multiply it by two terms, it will cancel because I decided to factor this one. And the last two terms, it's because of this one. It will be r2 plus jx sub 2 sum I sub 2. And so what I will do next, I will introduce this quantity, very important quantity, g. Sometimes it's called discriminant. This expression in the bracket. And so by introducing this notation, I can write the formula 21 in the more simple form. So v sub 2 will be equal to this first term plus this second term instead of the expression of the bracket, I use d I sub 2. So I found how the secondary voltage across the load, depends on the current, which is due to the load, and the primary voltage, which is applied due to the electromagnetic current. And now I will start investigation of this term, analysis of these terms. So first I would like to understand that v sub 2 is a sum of two distinct terms. So I would like to understand the physical meaning of the first term and the physical meaning of the second term. So what is the physical meaning of the first term? It's easy to understand. That if the secondary winding is open, no load, I sub 2 is equal to 0, then in this case, so if I sub 2 is equal to 0, then in this case, the secondary voltage will be given by this expression, by the first term. And you can immediately ask me, Professor, why did he put this IND? Because if the secondary voltage is induced, if there is no load, secondary winding is open. So it's like, oh, so what will be? Still will be the voltage across the terminal of the secondary winding if it's open. And it will be given by this formula. And this secondary voltage induced physically because the primary voltage creates a primary current, it creates magnetic field lines, creates time varying magnetic field due to these lines, and this time varying magnetic field induces voltage. And so this will be this induced voltage due to the coupling between the primary and secondary winding. Then, what will be the meaning of the second term? This is the expression for the second term. And I put here superscript drop. What it means physically? That represents the drop of the voltage due to the load. The load results in some current, and consequently the drop of the voltage across the voltage across the secondary winding when there is a load is not equal to induced voltage. It will be this term, which is due to the load because due to the load current I sub 2, and consequently an additional drop of the voltage. Now, what is the significance of this term? I said many times during this course, and I will repeat again, that one of the main challenges of power system is to design them in a such way that we will provide the power to our customers with more or less constant voltage in the face of continuously and predictably changing load. I said it many times, and I repeat it again. And the continuously and predictably changing load is a change of this current, which is due to the load impedance. And the change of the voltage, this term will not change. It's constant. The change of the voltage is due to this term, due to the drop of due to the load. And for the transformer to be a very good transformer, to satisfy this condition, that we can provide the power to our customers with more or less constant value of the voltage in the face of continuously predictably changing load, this term should be small. And it will be small if this D is small, if this D is small. So in this sense, this D determines the quality of the transformer. To what extent the transformer can maintain the voltage across the terminal of the secondary winding in the face of continuously predictably changing load. Continuously predictably changing load. So this D determines the property of the transformer, the quality of the transformer. The smaller the D, the better the property of the transformer. But in life, whatever you will get, you will have to price for this. You have to pay a price for this. What will be the price for this, for small d? The price for this for small d will be due to the situation when accidentally we will have short circuits of the secondary winding. So we will consider the short circuit of the secondary winding. What the short circuit of the secondary winding means that this voltage is equal to 0. It's highly undesirable regime that this voltage, short circuit in a cell that is equal to 0. Current, this will be short circuit current, and I can, so what I will do, I will move this term over there, this 0, I will move this term over there, and divide by this, and I will find this short circuit current. So it will be, when I move it over there, that will be J x sub 1, 2, divided by R sub 1 plus J x sub 1, 1, multiplied by R2 plus J XR22 times D and times V sub 1. So this will be the short circuit current. And we can see the smaller the D, the better the quality of the transformer, the more it's sensitive to the short circuit situation. It results in larger short circuit current. So there is nothing fantastic. If you would like to have a very good quality transformer, that is maintain more or less constant voltage in the face of continuous or predictably changing load, you can achieve this by using small d, but then you should pay for very good protection system, relay protection system, to switch it off very fast during the short circuit situation. But whatever it is, we can see that this parameter d determines the property of the transformer in power engineer. It determines its ability to maintain more or less constant voltage in the face of continuous or predictably changing load, and it determines its sensitivity to the short circuit situation. So this parameter is very important, D. And from now what will come? The analysis of all this D. What this D depends on. And it turns out that it will depend on leakage inductances. So it will depend that we did not neglect this psi sub L. We neglected in the case of the in the ideal transformer, that it will depend on leakage inductances. It will depend on leakage inductances. And so there is next discussion, which is called leakage inductances. So first I will start with the definition of inductance, the primary inductance. So what is the definition of the primary inductance? You will consider the situation when there is only the primary current and the secondary current is equal to 0. This primary current will create magnetic field lines, and so they will be coupled to the terms of the primary winding, and they will form what is called flux linkages. They will form flux linkages of the primary winding due to the current through the primary winding. And we will divide by the current, and this will be your inductance. And if you will read it in my book, you should know this from 380, that inductance does not depend, strictly speaking, on the flux linkages and current. It depends on the number of turns, usually it's proportional to the square number of turns if you neglect displacement current between the turns, which is not always the case when you deal with high frequency application, especially when you deal with integrated circuits. But anyway, this does not depend on the flux linkage, it doesn't depend on current, it's coefficient of proportionality between them, it depends on square number of turns, it depends on magnetic permeability of ferromagnetic core, and it depends on geometry of the ferromagnetic core. But these flux linkages has two distinct components. One will be the flux linkages due to the flux through the ferromagnetic core. Flux which is due to the magnetic field lines which entirely confined to the ferromagnetic core. And this ferromagnetic core flux will link all turns of the primary winding because they're all confined to the ferromagnetic core. So it has two terms, 1 sub 1, phi sub c, is the flux through the ferromagnetic core due to the primary current. And then it will be leakage flux due to the primary current. And you will divide this by I sub 1. And you will split this fraction into two fractions. And so the first term you call the main inductance, main primary inductance. It's called main because it's main component of the primary inductance. It's the largest part because it's due to the flux, which here is due to the most magnetic field lines, or the small field lines leak out. And the second term is called leakage inductance. It's due to the magnetic field lines which leak out and create flux linkages. And so if you will substitute in this formula, you will find this result, that the total inductance is the sum of the main inductance plus the leakage inductance. So in a way what happens? That the total inductance is due to the sum of the main inductance, which is due to the most of the magnetic field lines which confine to the ferromagnetic core due to its high magnetic permeability. Small number of them will leak out, they will also create flux linkages, and this will be the leakage inductance. Similarly, you can consider the second inductance. So you assume that the current through the primary inductance is 0, and only the second coil, second winding is energized. There is current I sub 2. This current will create the magnetic field lines. These magnetic field lines will link the terms of the secondary winding, and they will form the flux linkages of the secondary winding due to the current through the secondary winding. You see, because I'm dealing only with the secondary winding, I use here two subscript 1, 1 when I deal with the primary, and 2, 2 when I deal with the second. Again, these total flux linkages can be separated in two distinct parts. One part it will be due to the core flux created by the secondary current. And this flux will link all terms of the primary winding because all of them confine to the ferromagnetic core. And then it will be additional term. It will, so due to the magnetic field lines which partially leak out, and they link the terms of the secondary winding divided by I sub 2. And again, now you can write that L sub 2 has two distinct components. One is a main inductance, and another is a leakage inductance. And the main inductance is the first term. By the leakage inductance is the second term in formula 39. So far we discussed inductances. Now we will go to the discussion of mutual inductance. How we define mutual inductance? You studied this in electromagnetic field theory, you studied it in physics, 380, the class E and E 380. We will excite the first winding, so there will be some current I sub 1 through the first winding. and it will create magnetic field lines, and it will link the secondary winding. And so that this will be equal the flux linkages of the secondary winding due to the current in the primary winding. And mostly it will be linked by the magnetic field lines go through the ferromagnetic core. So this will be equal n sub 2 is the number of the turns of the secondary winding times the flux through the ferromagnetic core created by the primary current. And then I will do the following trick. I will multiply then divide, or divide and multiply by n sub 1. And then I will go to this formula. You can see the second factor here is nothing else as a main, the second factor is nothing else as a main inductance of the primary winding. And this ratio is nothing else as reciprocal to the turn ratio. And from here I can find that the main inductance is equal, I will multiply by A, is equal A times mutual inductance. So I considered mutual inductance when I excited the primary winding. Now I will consider mutual inductance. It will be the same when I excite the secondary winding. Then this mutual inductance will define as the flux linkages of the primary winding due to the current through the secondary winding. And these flux linkages will be by and large due to the magnetic field lines which go through the ferromagnetic core. So it will be due to the core flux created by the secondary winding, which is excited, divided by I sub 2. And then I do similar trick. Then I will do similar trick. I divide and multiply by n sub 2. And then I will go to this formula. So the second term, you can see it's nothing else as a main secondary inductance. And this is the turn ratio. And from here I can find what will be the secondary inductance, main inductance. It will be 1 over A, so I will divide by A times mutual inductance. Then I will go to these formulas, 38 and 40. According to 38, this main reactance is equal to the difference of these. But at the same time, this main reactance is equal to AM. So you can write that AM, which is the main reactance, will be equal to total primary inductance minus leakage inductance. Similarly, I will go back to this formula, and that secondary main inductance will be the difference of the total secondary inductance and leakage secondary inductance. But this difference is equal to 1 over A times M. And what I will do next, I will multiply formula 46 and 47. If I will do this multiplication, I will get that m squared will be equal. M squared will be equal this product and so this simple algebra, it will be equal L sub 1 times L sub 2 minus L sub 2 times L sub 1 leakage minus L sub 2 L sub 1 times L sub 2 leakage and plus the product of leakage reactants, inductance. And now leakage reactant inductance is a very small. So, but before, what I will do next, I will divide this expression by both sides, by m, divide by L1 times L sub 2. Then it will be here 1 minus the primary leakage inductance to the primary inductance minus the second leakage inductance to the secondary inductance and multiply the product of leakage inductances divided by L sub 1 and L sub 2. But leakage inductances are very small. It's because they do the small number of fill lines will leak out. So because of that, this term is very small. This term is very small. This term is very small. It can be neglected. So then you will write from here, is it neglected, that you will get 1 minus m squared over L sub 1 over L sub 2 will be determined only by the leakage inductances. So what I did, I moved this term over there and I moved it here. And it will be L sub 1 leakage divided by L sub 1 plus L sub 2 leakage divided by L sub 2. I'm almost there. Then I will go to the expression for D, which determines the property of the transformer. You can ask, Professor, what it has to do with the D? And where is my expression for D? My expression for D is formula 30. In the formula 30, as you can see, resistances are very small in comparison with reactances. So D, so R sub 1 is very small in comparison with reactances. And R sub 2 is very small in comparison with the secondary reactance. So if I neglect them, then I will find that D will be equal 1 minus x sub 1 squared. You see it will be j squared and then here jx sub 1 and jx sub 2. So j squared will cancel, so it will be x sub 1 2 squared divided by x sub 1 1 times x sub 2 2. And then I will use these formulas. I will use formulas 25. If you will substitute here, you will find that this D will be equal 1 minus m squared over L sub 1 times L sub 2. And it's equal to this expression. Consequently, D is determined by leakage reactances. So we achieve this result is that leakage reactances determine D, and D determines the property of the transformer. Its ability to maintain more or less constant voltage in the face of continuous and predictably changing load, and its vulnerability to the short circuit situation. So it means that these leakage reactances are very important. We deal with a situation when small parameters are extremely important. They cannot be neglected. And so what we will do next, we have to start with a couple circuit equations and how we should modify them that leakage reactances will appear explicitly. Leakage inductances will appear explicitly. And this also will lead to very interesting equivalent circuit of the transformer. By the time that, I apologize for me in the future lectures, and thank you very much for your patience, and we'll see you on Thursday.